And let's start with the second part of the lecture, and in particular to the way we can do it with the most common cycles, which are the steam cycle or ranking cycle. So in this lecture we will answer these questions. What are the heat sources that we have available in real life? We will see why in real life, what is a Carnot cycle, and why in the real world we do not use a Carnot cycle. And then we will see how in reality we can convert heat into work with a steam cycle. And we will discuss the principle, the components, and the ways to increase the efficiency of this cycle itself. So the lecture will be as follows. We will first start with a review of the thermodynamics. So we will see the main concept that we've seen before in the lecture. Secondly, we will define the last toolkit that we need, which is the thermodynamic diagrams. So this is the last thing that we need from the theory in order to be able to work on cycles. And then we will focus more in detail on the steam cycle and look at it using the thermodynamic diagram that we have introduced and that you have also on Moodle. If you see some graphs now on Moodle that you do not understand, they should be clearer at the end of this lecture. So let's start with a little review of what we did what we saw in the first hour of the lecture. So we said that we have the first law of thermodynamics that tells us that energy is not created nor destroyed, but is only converted and conserved. And then we have the second law that tells us that there are irreversibilities. Okay? And then let's just, I can show you maybe for a second on the blackboard this thing. So let's just recall the concepts that you need in order to, the efficiencies, the concept of efficiencies that you need to remember for the rest of the course. So if you have a cycle like that works between a hot and a cold source, okay? So there will be some heat. You remember we indicate with plus something entering in our system here in order to produce some work, and there will be some heat given to the cold source, okay? And you can use the dot if you're talking about power. You don't use the dot if you're talking about energy. So just to summarize what we discussed about before, the first efficiency we can calculate is the so-called first law efficiency, which is given by how much work we produce divided by how much input heat we have. Then Carnot tells us that if we have a cycle working between these two temperatures, the maximum theoretical efficiency that we can obtain with a reversible theoretical cycle is dependent only on the temperature and expressed by this formula. Okay? And remember, these temperatures are in Kelvin. Okay? And then you have the second efficiency, which compares the second law efficiency, we also called exergy efficiency, which compares how well we are designing the system. So what we compare there is the heat, the mechanical work we produce, compared to the maximum mechanical work we could produce in a theoretical cycle, which is, so this one is equal to the amount of heat times the first law efficiency. This one is equal to the amount of heat that is given times the Carnot factor. Okay? So these two go away. So the second law efficiency is the first law efficiency divided by the Carnot factor. So these three things, if you have clearly understood these three concepts, I would say you have the tools that you need to follow most of the things we will discuss during the course, and then we will be able to understand other technologies such as heat pumps, such as cogeneration units, because we will always be using this terminology in the course. So it's like learning to speak the language, having the vocabulary for the course. So let's see now this Q plus that we have here. So the amount of heat that we have available. the first law tells us that this heat can be converted to electricity. Okay, so this was the main finding of the first law, understanding that heat and electricity are actually the same thing. They can be measured in the same unit, and one can be converted to the other, although work can be fully converted into heat, heat can only partially be converted to work. So how do we produce electricity? Starting from these heat sources. So the heat sources could be a geothermal source, could be the combustion of natural gas, the combustion of oil, the combustion of coal, the heat generated by nuclear reaction. So we have multiple sources of heat. We need a way to convert this heat into electricity. So the last tool that we need, the last thing that we need in order to be able to do this calculation are thermodynamic diagrams. So you remember from the lecture before that I said that when we have a thermodynamic system, we call system properties or state functions the properties that describe the thermodynamic state of a system and depend only, they are not process dependent. So they depend, if we have a process going from A to B, they depend only on B and A. They do not depend on the path. So you remember work and heat are not state functions, but temperature, pressure, entropy, enthalpy, and so on are. So Gibbs, another thermodynamicist from the 19th century, tells us one thing, one important law, which is that the so-called phase rule. It tells us that if we have a system in thermodynamic equilibrium and we want to characterize it, which means we want to know everything about the system, the number of degrees of freedom, so the number of variables we need to know, we need to fix in order to know everything about the system, is given by the number of compounds minus the number of phases plus 2. Okay? Let's say, for example, we have liquid water. So we have one independent compound, which is water. We have one phase, which is liquid. So 1 minus 1 is 0. We have 2. So it tells us that, for example, for water, we need only 2 variables to define its state in a given, we need only 2 variables to define the state if it is in a liquid state. And so on. If, for example, we are in the transition of phase, so for example, we are changing between liquid and vapor, then we have 1 here, we have 2 phases, so minus 1 plus 2, 1. So for boiling water, we need only 1 variable to know. So why is this number 2 important? This rule of phases, why is it important? It's because we can show that for any closed system in thermodynamic equilibrium, for any set of 3 state variables x, y, z, we can define a state function that relates the 3 variables, which means that if we know 2 state variables, we can calculate all the other state variables. So, for example, you might know the famous, you might remember from your previous studies the famous law of gas, so PV equal RT. P, V, and T are the 3 variables. If we know 2 of them, we will know also the 3rd one, okay? And this works for every state function of closed system in thermodynamic equilibrium. What is the consequence of this? Since we have 2 variables, we can plot the properties of system in what is called thermodynamic diagrams, okay? So every property of a system can be plotted on a 2D diagram. One of the most used diagrams is the so-called temperature entropy diagram, okay? So it's called the TS diagram, and let's see a generic cycle. Now I'm taking a generic cycle, which is actually, now you discover what a Carnot cycle is. I talked about that before, but I did not characterize it. So let's take a generic cycle in which we have some heat input, some heat output, some work input, some work output. In particular, and we represent it on a temperature entropy diagram. The Carnot cycle works like this. So first, we have a heat addition, an input of heat at constant temperature, so an isotherm, which means same temperature, at temperature high, so at the highest temperature. The second part, we generate work through an adiabatic expansion. Adiabatic means that there is no heat exchange, so only work. and is also isentropic because we have the same entropy on this axis. Then we condensate the fluid in order to reject heat to the cold source, which is normally the atmosphere in our cases. And then we go back to the initial state by giving work to the system, normally with a pump or a compressor, depending on the type of system, okay? So this is the way we represent a cycle in a thermodynamic diagram. Why is this representation so interesting? If you remember what I showed you before, for a reversible cycle, we can write this equation. We can write that the differential of the heat is equal to T in the S. So if we integrate this equation, we see that the area, that the red area here, is the amount of heat that we are giving to the system. Okay? This means that in the same way, the heat that we are rejecting from the system to the cold source is represented by this area. So now if you remember the first principle of thermodynamics that tells us that everything that goes in goes out, with the net amount of work that we can produce in a cycle, with a cycle, is the red area at the center of a cycle. So that's why that's why TS diagrams are so used in the practice, because if we take a TS diagram, by looking, we draw the cycle on the diagram, we're able to see how much work we're producing just looking at the surface, at the integral of the area within the cycle. Okay? And we can see that now I showed you this for reversible processes. This concept of the area representing the work is also valid for irreversible processes, and you'll see why later. So this is the diagram you have now on Moodle. You can also give a look if you have your laptop right now. So as I told you, this is the TS diagram of water. So here in this diagram we have all the properties of water that, as I told you, if we have two characteristics, so if we're able to define two of the state variables, we can know all the others. So let's give a look at how to read this diagram, okay? So you see on the y-axis we have the temperature, in this case expressed in degrees Celsius. On the x-axis we have the specific entropy expressed in kilojoule per kilogram Kelvin. And then you have different lines. So all the different lines are drawn by fixing one state variable, okay? So the horizontal line here is constant temperature lines, okay? The vertical lines are obviously constant entropy. Being a temperature to entropy diagram, it makes sense. This was not expected, this is not supposed to happen. Then you have lines at constant volume, the so-called isocores. So all these lines, the dotted lines here, that you see here, are lines at constant volume. Then we have the constant pressure lines, which are these ones in this case. So the ones that you see, for example, indicated with P. We have also the constant enthalpy lines and the constant humidity. Humidity defined as the amount of liquid water into a liquid vapor phase. So looking at this diagram, we can study every process involving water. For example, you know that water boils if water is at the pressure of 1 atmosphere, you see, pressure 1, you know that water boils at 100 degrees, right? So if we start here with liquid water at 30 degrees, we first heat it, then we evaporate it, we get here to the saturated vapor, and then we can increase the temperature even further. So I think you have this diagram on Moodle. Try to give a look if you have your laptop with you, so if this one can answer the people that have the laptop maybe with them. So if I'm asking you, if you look at the diagrams that you have on Moodle, if you put on that diagram P, the pressure, equal to 10 bar, what is the boiling temperature of water? And even if you don't have a diagram on hand, if you have any cooking experience at home, you should be able to answer this question, I assume. Okay, so who's still calculating? Raise your hand. Okay, so still some time. Okay, so let's see if you normally cook at home. Yes, you do. So, as you see, so this is the way to interpret this diagram. What you want to know, let's go back to the diagram here. What you want to know is that when you have around 10 bar, the temperature here is around 185 degrees or so on. So this is the principle when you cook, for example, you have this pressure cooking pan at home. You don't get to 10 bar there, you get to, I think, something like 2-3 bars, and then the temperature raises to 120, 130 degrees, which allows you to cook your food faster, right? So, in the diagram, so in this diagram of water, which we will familiarize, you have an exercise also in which you have to use it. You can distinguish 3 phases. So the liquid phase of water is here, is the left-hand side of the diagram. Inside this bell, it is called normally the bell, is the liquid plus vapor phase. So in this phase, we are slowly boiling, for example, water. So here we have full liquid. Here we increase the X, which is the humidity of the water. So we basically increase the amount of steam until we go here and we have saturated steam, okay? At 100 degrees in this case. So it means we have full steam in thermodynamic equilibrium. And you remember before I told you that given the rule of phase, when we are on this line, we have 2 phases, so it means we need only one variable to characterize the system. Actually, if we know the temperature on the entropy, is enough because we have this line characterizing the system. And then in this part here, we have the vapor phase. This point up here is the characteristic phase in which all the phases are in equilibrium. It's called the supercritical point of water. Above this temperature and pressure, you cannot distinguish between a liquid and a vapor phase of water. And it's at around, if I remember well, 220 bars and almost 400 degrees. So this is called the supercritical point. So, as I told you before, based on the first law of thermodynamics for open systems, let's see what happens when we heat water. So you remember this law that we learned in we saw in the first lecture. The amount of heat that we transfer to a system is given by the mass flow by the difference in enthalpy. And this relation that I told you is valid for every system, even irreversible processes, tells us that the variation in this diagram, in this TDS diagram, is proportional to the variation of enthalpy. Okay? So here we see that if we're heating a liquid, water in this case, at 5 bar, from 35 degrees to 275 degrees, we start here at 35 degrees. We increase the temperature with sensible heat addition. We reach a temperature of around 160, 150 degrees. At this stage, we boil the water. We boil the water at constant pressure and constant temperature, right? Latent heat of phase exchange, And then, when we have full vapor, we can superheat the vapor. So this is the way, quite simple, that you have to use these diagrams, okay? And if you have a point lying between two, so often when you have to do manual calculations, so you can use software for this. There are software that do this automatically, and we normally use that when we do our work nowadays. It's not we go all the time in our algorithm to go check by hand. But when you do the exercise, it's a good exercise to do at least once. That's why we give it to you in the course. If you have to interpolate between these 2 points on the same line, you can, for example, in this case, we want to know the enthalpy here in between these 2 points. You can use the interpolation here, which is useful in the exercise. So let's now discuss about the steam cycle. You remember from the previous lecture that I told you about the Carnot theorem. So Carnot tells us if you want to build the best cycle you can have, then you should build my cycle, the Carnot cycle, right? So if we know that this reversible ideal cycle is the best we could do, and is the one I showed you before, why? Because it's the one with the highest theoretical efficiency. Why don't we use it in reality? So this would be the first thing that we might think. So let's see how the Carnot factor looks like on the diagram I showed you before, on the TS diagram of water. So if we represent it this way, so we can fit the Carnot factor below the bell of water. So we have a compression between 0 and 1. We have a generation of steam between 1 and 2 at constant temperature. We have an expansion in a turbine at constant entropy and no heat exchange. No heat exchange. And then we have a condensation at the lowest temperature. The problem is that we have practical constraints to build this cycle. It does not work in reality. Why doesn't it work? Well, first of all, because if we want to remain inside the bell, so we do not to go over the bell, as we normally do, you'll see that we do later, then we are forced to use a quite low T1, so we do not exploit fully the increase of temperature that materials allow us. So steel and so on, they can resist higher temperatures. So that's why we don't do it. The second one is that here, if you remember, we have a mixture between liquid and vapor. So if we want to compress a mixture of liquid and vapor, it's a complicated process to do because a liquid is compressed by a pump to increase the pressure, right? So not compressed. A liquid is the pressure is increased with a pump. And a gas is compressed with a compressor, but compressing the two together is impossible, I would say. And then, also, having water here at the exit of the turbine, so point 3, is also problematic. So, as you see in the real cycles, we try to go out of the bell if we can, because having the coexistence of liquid and vapor is a problem in practical applications. And then another thing is that in this process from 1 to 2, we assume that heat is given at a constant temperature. And this is not the case. When we have combustion or so on, when we get heat, we normally have a decrease in temperature of the source that's giving us heat. And actually, I did not go through it in the previous slides, but at the end of the last lecture in the slides, you have an example of how to take this into account. It's called the log mean temperature. And you'll see it in the exercises, but this does not again represent reality. So that's why, in reality, we use the so-called Rankine or steam cycle to generate electricity. How does it work? So on a TS diagram, it looks like this. So remember this equation, always the same equation coming from the first principle. There are 4 phases. First of all, the fluid, which is water, so you have a cycle like this, the fluid here is water. First of all, we take the water from point 1 to point 2, and we first heat it, then we boil it, and then we superheat it. And this is what happens inside the boiler. Then, when we have taken all the heat from the source, we have a very high temperature and very high pressure steam, so very precious material. At this point, we expand it in the turbine. So we expand the steam in the turbine in order to produce work and electricity. In theory, it should be a straight line here is entropic, but as I told you, in reality, and as we'll discuss later, this is not the case, so we cannot have isentropic expansion because entropy increases. And so we have an expansion in the turbine that follows this line going towards the right. Then we condensate the steam in order to go back to have liquid. So, and that's where the condenser comes in. Okay, in this way we release heat to the environment. At this point we have liquid again, and so we can pump it with we can pump liquid with a pump to increase the pressure and close the cycle. The first law efficiency of this cycle is calculated in this way. Again, is the amount of work we produce divided by the quantity of heat we have to put with the combustion and so on. In some cases you will see that we put at the numerator also the amount of heat, the amount of work that we need for the pump. I have to tell you, normally this work is quite negligible. So that's an advantage of a cycle. Pumping water is negligible, it's the order of 1 or 2% compared to the work you get in the turbine. So in some exercises you'll see that this part is neglected. So, and the normal efficiency, for example, of a coal power plant works in this way. You burn coal in the boiler, you put fuel, you have combustion, and you get the heat, the Q plus comes from coal, you expand it in the turbine and so on, and you keep producing electricity in this way. Okay? And thanks to the relation of Gibbs that tells us that in a real process, we can apply this formula. When we give heat, and we take heat from a system at constant pressure, the derivative of a constant goes away. And so we can also, for the irreversible real cycle, the amount of work that we can produce out of the Rankine cycle corresponds to the red area here. So that's why the TS diagram is so used, because you just have to draw the cycle on the diagram, and the area already gives you an idea of how much work you'll be able to produce. So this is how a system looks like normally. So, as I told you, you have the pump that pumps liquid to increase the pressure, using the heat from the combustion normally, or boilers, but not necessarily combustion. You increase temperature and pressure, you then expand it in a turbine, and then you condense, to release the heat to the environment, you condense the steam to go back to liquid. If we look at the components, you might have seen, if you have passed by the mechanical engineering department at TPFL, you have a big turbine there, right? So that's a steam turbine. And it works with a principle which is basically this one. So you start from having an inlet at high temperature and pressure, then the liquid, the steam is expanded in the turbine. By expanding the steam, the pressure reduces, the volume increases. That's why you have an increase in the section of the turbine, okay? And the force given by the rotation of the rotor caused by the expansion of the steam makes the crankshaft, makes the shaft rotate. And this is normally connected to a gearbox, and the gearbox is the one that converts mechanical work then into electricity. So that's how a power plant works normally. And there is one note that we have to make. So as I told you before, expansion in a turbine should be isentropic in theory. So if we don't have losses, it should be the real line here. But in reality, in real world process, we have an increase of entropy. So if we expand something in a turbine, this will be associated to an increase of entropy. So that's why we have the real path is not between 2 and 3s, it is between 2 and 3. So this allows us to define one important characteristic of cycles, which is the isentropic of turbines, which is the isentropic efficiency of a turbine, or the isentropic efficiency of a compressor. To show it, normally we use another diagram that you also have on Moodle, is the so-called Mollier diagram, is an enthalpy-entropy, HS diagram. Why do you use this diagram? Because on this diagram, enthalpy is on the axis, so it's easier to measure. That's basically the reason why you use it. So you can see that in a isentropic expansion, here on the left, you would have more enthalpy, you would produce more work. In a real cycle, you have losses, so you produce less work. And to calculate how much it is, you basically have to take the HS diagram and measure, based on the starting and the ending point, how much the expansion is. And normally what you have in the exercise and what you have in reality is that you first calculate what the ideal would be. And then I tell you, look, the turbine is 90% isentropic efficiency. And so you take that value that you calculated, this one, you multiply it by 0.9 and you go find in the diagram the point that corresponds to that characteristic, okay? Because the pressure here, you are on an isobar, same pressure. So this is the formula that you will use also in the course, in the exercises. Normally, isentropic efficiencies can be pretty high. In very good power plants, they can be above 90%. If you want to save on construction equipment and so on, because you want a cheap system, then it can go down to 70–75%. So the last part before the exercise is how we can increase the efficiency of this cycle. So normally, the cycle that I showed you is the standard ranking cycle, and it has an efficiency of around 35–40%. This efficiency can be increased by doing different things. So there are normally 5 actions that you can do to increase the efficiency of a ranking cycle. And let's see them here. The first ones are increasing the vaporization. So the first one is to increase the vaporization pressure or increasing the superheating temperature. So here you have 2 limits to face. The first one is that you cannot go above the critical point. Actually, you can go above in practice the critical point, but the problem is that at that point you will not have a straight line in the graph. You have a line, you have a difference in temperature while the phase changes. So this is a problem when you build a heat exchanger, because if you have a phase change in which the temperature changes, it means that you have your heat exchanger which is submitted to thermal stress because of a temperature difference between one point and the other. So that's why in normal cycle with water, you never go above that temperature. And then you have the limits of materials. Of course, you would like to go high, you could go up to very high temperature, 1500, 600 degrees, because that's the temperature of combustion. The problem is that these materials would be extremely expensive and they might not be worth it. So that's the limit. And the second one is decreasing the condensation pressure, which basically means that you can reduce this line, but of course you are limited by the source that you have. That's why normally, when you have a lake or a river available, you tend to use it. Why this? Because you have good heat exchange, and in the lake, if you go down like some meters, like here in the lake, you have a source at around 6–7 degrees. So if you can lower the temperature, it is better. And that's actually what they do at EPFL. At EPFL, there is a heat pump system and a gas turbine system that we might able to visit. I forgot about this year, but in last years we were visiting. So we'll try to organize a visit there. And this is a system that uses the lake as heat source because it is a constant and low temperature, right? Then you have 3 other systems that you can do, and then they can be combined. So one of them is to draw off some of the steam at medium pressure here during the expansion of a turbine and use it to preheat the liquid. So overall, this is a sort of cogeneration. You use part of the steam that you draw off the turbine, so you don't go with all the steam to a complete expansion. You stop a bit before, and that allows you to use this heat to, you see here, so you extract the steam, and you use it to preheat the liquid out of the pump before it enters in the boiler. So this kind of system overall has a positive energy balance, and it normally gives you an increase of the efficiency which is in the order of magnitude of 7%. Additionally, what is normally done in cycles is superheating multiple times the liquid, which means you have an expansion in the turbine, then you go back, you exit from the turbine, you go back in the steam generator in the boiler, and you use again the heat from the boiler to superheat again the fluid. So this is a better way to exploit all the heat available by the fumes. And actually in real cycles, if you look at the real diagram, you have multiple superheating. Normally this is done to increase the efficiency and to make the heat exchange more efficient. And this again allows you to another 5% increase over the 7% that you have. And the last thing you can do is that if you do both draw off and re-superheating, if you look at the composite curve, if you look at the diagram of how you give heat to the cycle, you see that overall you have some free available heat that you can also use to heat the air, to preheat the air of a combustion in order to increase the efficiency of the combustion. So overall, if you do these three actions, you can increase the efficiency of a cycle by around 20%. And here, of course, you have a trade-off between the cost that you have by doing all these modifications to the cycle, which means having a more complicated system, having a regenerator, having more heat exchangers, and the gain in efficiency that you have. Normally, real cycles that you see in real life, in real applications, have almost all of these enhancements because it's worth doing them. And the last thing is that, so today I described you the steam cycle and how it works. The same exact principle, the same exact structure can be used also for other cycles, not using steam, not using water. Normally, in geothermal application, when you have a low temperature heat source, you want to use organic fluids that have a lower boiling point than water. This allows you to exploit, to recover heat from low temperature heat sources for which water, the boiling point of water would simply be too high. So normally when we have geothermal application, heat recovery in cement plant and these other applications, what you have is you use organic fluids and this allows you to recover the heat at lower temperatures. Important to say, the equations and the structure is the same, but the diagrams are different. So if you use another fluid, you need to go and find the diagram of that fluid. For example, it could be, in the case of refrigerators, you use R134A. That's a quite common fluid that is used. In geothermal, you can use toluene or other fluids that are better for this application. But if you want to apply it to that, you cannot use the TS diagram of water, you have to use the TS diagram of that fluid. So again, the message that is today is that the key part is to understand the basics of thermodynamics that I also recalled before on the blackboard. We showed why we cannot use a Carnot cycle in practice. And we showed how a Rankine cycle, a real steam cycle works and how we can increase its efficiency. So today, the idea is that we recommend you to stay in class for the last hour. And now, the exercise that I showed you before, the exercise 01 that you have on Moodle, is the one that you're supposed to solve today in class. And we're here, I'll also be here together with Sian, to help you solve this exercise so you can ask questions and so on. On Moodle, you have also another exercise, which is the 03. So it's the exercise 3 is on the Rankine cycle. The idea is that you solve it at home during this week, and next week you come here and you ask us questions after having tried to solve it alone. And on Moodle, Francois also just added a tool called SpeakUp. So as I told you before, if you have questions about the exercise or the theory, do not hesitate to post it on the SpeakUp. So we will check these questions and we will start the next lecture by answering these questions that you have. So with that, if you have questions, otherwise I leave you to the exercise.